Well, first of all, thank you very much for coming here today. We at 247Solar are very honored that Masdar Research and Masdar Corporation are enthusiastic about working with us. Really appreciate that. I also want to thank you all for being here. There are many of you I don't know, but in the audience we have partners, prospective partners, and prospective customers, and it's very exciting for us to see you all here. In particular, I'd like to acknowledge DK Solar, our Chinese partners, sitting in the back of the room. Maybe you could wave. There you go. And look forward to working with any of you who would care to join us in the future. Some of you know a lot about CSP, and some of you are relatively new to it. What you'll see here is an approach that really stands on the shoulders of others who've gone before us in CSP. There are some innovations that we came out of our minds, but had not others gone before us, we probably would not have had these ideas. Those of you who do know CSP have some attitudes or thoughts or concerns or issues that you associate with this technology. And I'd like for you to be thinking about those as I present and see whether or not we check the box of addressing your concerns. Those concerns, for example, might be cost. They might be flexibility of operation. They might be the long project times that these big projects take. There are a whole range of things that people are concerned about when they think about CSP. So what I'd like to do here is show you a new approach that we anticipate will be tested here at Masdar. And what we appreciate so much about this is that both Masdar Institute has really become, in a sense, a technology gateway to the Middle East. They have achieved a very spectacular credibility and reputation in a very short period of time. And of course, Masdar Corporation is one of the major players in the financing of clean energy projects all over the world. And by the way, please do, before you leave, come and look at the model up here. There's also a brochure. Please feel free to take a copy with you, or more if you have people to share them with. So our target is coal competitive 24/7 solar power. Now why is that important? It's important because there aren't any other clean energy technologies that can operate 24/7 firmly, dispatchably, reliably, and flexibly. So in many ways, this is a revolution in an approach to concentrated solar power. This technology has its origins at MIT. The US Department of Energy partially funded the development of this technology. It's competitive with PV, but in fact, it's reliable. You can count on it. And it actually stabilizes the grid rather than destabilizes it. And it operates all the time, not just when the sun is shining. Our target is to be competitive with coal. And of course, we're at the top of our cost curve to begin with, and we won't be competitive immediately, but compared with big power plants, you can operate this flexibly. As you'll see, it's a modular system, so you don't have to bring on 200 megawatts all at once or bring it down all at once. These small turbines, as I'll show you in a few minutes, start up very quickly and adjust very, very rapidly to changing demand. Very little outage time. You talk about capacity factor. A capacity factor is the percentage of the year that a power plant produces power. With a modular system as ours is, if one of the modules happens to be down for any reason, you may have dozens more that will still operate. And unlike any other power plant in the world, we can possibly achieve 100% capacity factor compared with maybe 20% for PV, maybe 35% for wind, 60 to 70 or maybe 80% for coal, and maybe 80 or 90% for nuclear. And by the way, one of the important benefits of that is that when a big power plant goes down, you've got to have another one sitting ready to operate. And so that's a huge savings for utilities. The majority of the components are factory made. We took a clue from wind and PV. Why have wind and PV costs come down so quickly? Mass production. Why do coal plants and nuclear plants keep going up in cost every year? Because they're on-site construction projects. And so we believe that there are opportunities for very attractive returns to project developers. Here's a little bit about myself. I first got started in solar energy in 1973 when I did my master's thesis at MIT on solar energy. And this has been a passion of mine. It's a passion not just because energy is important and fundamental to life, but because we strongly believe that solar energy can make all of our lives better in the future with lower cost clean power. My colleague, Joe Perry here, is a veteran in power generation. He's our Vice President of Corporate Development. He's got a range of very, very serious leadership and business and technical expertise and experience over the years. As I said earlier, the problem is that there are few low-cost, utility-scale, 24/7 clean electricity solutions. When you think about the alternatives, PV, wind, and tidal, they're intermittent. Geothermal is risky. The geothermal source often drops shortly after you start up a geothermal plant. Capacity factors aren't anywhere close to 100%. It can't be considered base load. And nuclear power is very expensive. Current CSP can operate 24/7, but as we all know, the biggest challenges with current CSP is trying to get those costs down to where they're competitive. And everyone's trying really hard. The costs are coming down, but it is a huge challenge to get the cost down with conventional CSP. So we think of our approach as the next generation of CSP. So this technology, it's pre-engineered, just like a wind machine is pre-engineered. So every module is identical to every other. If you were to have a wind farm, every wind machine is identical. You have a 247 solar farm, every module is identical to every other module. And so it is competitive with PV, but much superior performance. I've gone over most of the characteristics already, but this is the short summary. What I haven't mentioned, and which is so important, is that we use water only to clean the mirrors. There's no other use of water, unlike steam turbines. We also don't use molten salts, unlike conventional CSP for storage. We use fire brick, as you'll see in a minute, which is nice and cheap. And we don't use any oils to transport heat. We just use air. This is one of my favorite quotes from one of my professors at MIT. If you want to make something cheap, make it from dirt. And when you think about our storage system, we use fire brick. So I like to put that up there just to make that connection. As I said earlier, the U.S. Department of Energy really likes this approach. They funded us very generously to help us develop the technology. We had a phase 1 engineering and cost feasibility study that cost us about $1.5 million. I'm going to show you our partners who helped us work on this. It was a 12-month study, and it demonstrated the technology and potential and the cost targets that are achievable. And then the second report covers the development of some of the technology. So the major breakthrough compared with conventional approaches to Brayton power towers, and the word Brayton is distinguishing from Rankine cycle. A Rankine cycle is a steam turbine. These are just thermodynamic terms. And a Brayton cycle is an air cycle, like a jet engine. Okay? So we did not invent the concept of a Brayton power tower. The existing approach to Brayton power towers is what is called, described as high pressure. In a high pressure Brayton tower, the compressor air of the turbine goes through the solar receiver. The disadvantage of that is that the solar receiver then is a pressure vessel. And because it's a pressure vessel, and I'll show you in a few minutes, the solar receiver has to be very, very small. And again, I'll explain why in just a few minutes. And the entire system is under high pressure. Expensive, complicated, even risky because of the high pressures. Have safety concerns. What we introduced is low pressure. And the way we came up with this concept was that we were developing a couple of MIT technologies. One of them was a high temperature heat exchanger. And we had this sort of aha eureka moment when we realized that this high temperature heat exchanger could be inserted into a conventional high pressure system. And instead of, it's hard to make this simple, and bear with me, but instead of having to send the high pressure air to the solar receiver, we are able to send basically ambient pressure air from the turbine to the solar receiver. Now the solar receiver is no longer a pressure vessel. And our initial baseline, first generation, low pressure receiver produces 7 to 8 times more energy than the high pressure solar receiver. So here is the conventional high pressure solar receiver. There were 2 organizations, the DLR, German Aerospace Center in Germany, and the Weizmann Institute in Israel. And they're both on the same track, and they both had the same problems. On the top center there is the word quartz window. It's pointed to a piece of glass that, as you see, is spherical or hemispherical going inside. I'm going to move over here for just a minute if I could. So you've got the quartz window like this, and that's holding the high pressure air in here. And the light's coming through here, and the air comes around the perimeter, comes in the sides, and comes out through a silicon carbide foam. And that foam is the absorber. That foam is the absorber and gets very hot to about 1,000, 1,100 degrees centigrade. And the air goes through it because it's foam, a lot of surface area, and comes out the other side between 950 and 1,000 C. Again, high pressure, but the important point here is that the aperture, the window is only 60 centimeters, only large enough to power 100 kilowatts, and not large enough on top of that to store any of the heat for nighttime off-sun uses. And such a system then can only compete against photovoltaics, because it only operates when the sun shines. By having a low pressure solar receiver, we made the aperture about 2 meters in diameter. So the glass is much, much larger, letting a lot more light in. Much simplified. Instead of having 3 active cooling systems to make sure that the high pressure solar receiver doesn't deteriorate, we have none. We don't need any active cooling systems. This is a passive solar receiver. The only thing that moves is the air through it. So, like I said, no moving parts. There's an example of our prototype looking at it from the outside. Our thermal storage is also extremely simple. It's based on 100-plus-year-old technology that's been used by the steel refining industry and other industries for reclaiming heat. And typically, these are very large silo-looking devices filled with fire brick. They're only a fraction of the cost of batteries. These can be sized to generate power just during peak times, 3 hours, or for 24 hours. They're 3 to 4 feet in meters in diameter, 7 to 9 meters tall, filled with fire brick, pretty hot operation, no moving parts, very simple, reliable, long life. There's very little to go wrong, almost unlimited cycling. So here's the whole system, and you can see these various parts up here. Of course, the heliostats in front of the tower that has some air ducts in it to supply the air to the top, and then the hot air coming back down, the receiver sitting on top, and the thermal storage sitting next to it. And then what we call the 247 solar power block. The power block, of course, is what produces the power. And that takes the heat from the sun, and it's that heat that drives the turbine by heating the compressed air. For those of you who appreciate these kinds of diagrams, these are all the pieces. There are no other heat exchangers, valves, piping, anything else over and above what's shown here. These are all the pieces. So there are very few pieces to this simple system. So during the day, the blower here delivers the air from the turbine up through the solar receiver, comes back down. Some of it goes through the storage system, and some of it comes back down to power the turbine. At night, the solar receiver is turned off, and the airflow is reversed through the storage. Reversed through the storage, comes in at the bottom instead of the top, and takes the hottest air out and delivers it to the turbine. Very simple cycle. As I said, this power block is a major innovation for us, but it uses what we consider the most versatile power generator in the world, a microturbine. This can be combined into many units, from a single unit to hundreds. So 400 kilowatts to hundreds of megawatts. That can be powered by solar or by a wide variety of fuels. In fact, we can use fuels as backup for when there isn't sufficient sunshine. They are firmly dispatchable. They're very simple, low cost to operate and maintain. Only 4 to 6 hours of maintenance per year, literally. It's not like a steam turbine, where you have to have literally a team of people to operate a steam turbine 24/7. You don't need anybody on site to operate this system. Highly efficient. The efficiency of this system will range from 38% to as much as 80%. The 80% gets there if you're using the waste heat. The waste heat from these microturbines can be used for a variety of things: industrial process, water purification or desalination, absorption chilling, crop drying, and that's an added benefit and added revenue source. And they're all factory produced for rapid deployment and low cost. So these are plug and play. This unit here that you see on the screen comes from the factory packaged. You bring it to the site, you sit it on a concrete pad, you plug it into the grid, you connect to the grid, connect it to a source of heat, whether it's fuel or solar, and it's operating. This isn't like a big steam plant where you're working in the field for a year or two to get it to operate and have countless numbers of pieces and whatnot to get it to operate. And in addition, there are just multiple benefits to the grid. Flexible operation, rapid response to fluctuating demand or fluctuating voltage on the grid. They respond to those fluctuations almost as quickly as batteries. If you're really interested in more information about microturbines, this is a good article, and it's a good point for me to say that if you'd like a copy of this presentation, just give me your business card afterwards, and just write on it, please send me a copy of your presentation. We also have a technology roadmap to continue to improve the performance and reduce the costs of the power. This technology is very scalable. It's interesting, a couple decades ago, the first wind machines were a few hundred kilowatts like ours, with a tower of 30 or 40 meters like ours, and today they are several megawatts, as many as 5, 6, even larger now. We are confident that this can go to 2 megawatts, and we haven't done the engineering to satisfy ourselves to give us 100% confidence that we even go to larger module sizes in the future. I also mentioned that we were working on 2 MIT technologies when we had this eureka moment. And one of them is a very, very high efficiency ceramic turbine. And then finally, there are a range of other approaches. For example, if we were to use a phase change heat storage material, it would significantly reduce the size of the thermal storage and the weight. It may have some other benefits. And there are other approaches for improving over a long term the continued performance improvements and cost reductions of this concept. So keep in mind, this is an early stage concept. And like many things that are early stage, there are continuous improvements that can be made over time. So let me compare our technology to others. This is a graph produced by a third-party independent research organization that was projecting the costs of power from PV and different approaches to CSP with and without storage. So the dark blue is no storage, and the light blue is with 14 hours of storage. The horizontal yellow dotted line are 2 approaches to CSP, one tracking, the other fixed. The shortest bars are in the center there. And that's what we're doing. Here they call it an air Brayton tower. So that's just one third-party opinion about the future. And with factory production, the CapEx of the system drops rapidly with volume, as you would expect from factory production. And these numbers were taken from work that was done by Worley Parsons during our first Phase 1 report for the U.S. Department of Energy. So even there we had third-party validation of the work that we were doing. They were one of our partners. Some of you may be wondering, well, how do we compare with PV and batteries? And it's a reasonable question. Well, batteries will remain at least 10 times more expensive than our thermal storage. And the best-selling batteries today are these two. And the cost per kilowatt hour from those batteries is shown here. For storing, the cost, the capex to store electricity. Ours is only $24. So even if the cost of batteries drop significantly, we will still be much lower cost compared with batteries. Now how about this comparison where let's assume you want power all the time from PV and batteries. Well, you have to build 2, 3, maybe even 4 times larger PV field if you want that power 24/7. And then you have to have at least 16 hours of battery storage. Now what happens on that second day with no sun? Where does the power come from? With our system, so the total here in this example is $9,000 per kilowatt to achieve that. And ours is about half that cost. So yes, you can do PV and batteries, but only to get through a few hours to be competitive. But if you want power all the time, and strangely people want power all the time, PV and batteries isn't going to cut it. Here's an example for South Africa, a load curve in South Africa. And what here South Africa is wrestling, with should they add batteries to the grid or what should they do, and how can they respond with these big turbines? Again, these big turbines having difficulty responding quickly to changing demand. Well, with the flexible operation of our system, we can track that line for line. We don't have to have too much power at one time and too little another time. And so for a large grid system, you don't really need the batteries if you have our system. Here's how we compare with other approaches to CSP. Obviously, the red is bad and the green is good. Across the top, the power tower, then the parabolic trough, linear Fresnel, and then our plant. Down the side are different characteristics: reliability, power costs, permitting, construction, commissioning time, custom versus standard engineering and construction, costs, skill level required, environmental issues, land type requirements, scalability. Some of these things have sort of may be obvious because of the presentation I've already made, but let me just give you one example on land. One of the big concerns with concentrated solar power is the land. For one thing, most approaches to CSP require perfectly flat land, which means if the land is not perfectly flat, you come in and with big equipment and you make it flat. And with a modular system, we can actually deploy on rolling hills. We don't need it to be perfectly flat. So there are actually heliostat designs that don't even bother, don't even break the surface of the soil, that can actually can be placed sitting right on top of the soil, so that without having with little or no damage to the land, without using salts or oils, these kinds of things. Our system, compared with other conventional power towers, is not likely to kill birds, which is one of the discouraging things about very tall power towers in the United States. We have not identified yet an environmental problem with our system. And then compared with all forms of power generation, again, green is good, red is bad. Here our system is on the left, PV and wind in the middle, and conventional power on the right, new conventional power. what I can say unequivocally is if our approach to solar were, I'll say, the standard conventional approach to producing power, large power generation systems wouldn't have a chance. Nobody, people would look at them and say, "Are you crazy? Why would we build anything like that?" And for all the reasons that are listed up here under characteristics. Finally, the localization of the factory-made components. A large fraction of the components can be made where in the country in which it's deployed. In some countries like China and India, 100% of the components can be made in the country. In some of the smaller, maybe African countries, the fraction will be, of course, much lower. We have a really strong team. I introduced myself and Joe. We have two other really strong members of our leadership team. We have great global partners who've helped develop this technology over the years, some of whom are still with us as we go toward commercialization. We have an incredible board of advisors. These folks here are respected veterans in the power generation business. They volunteer their time and advice in order to support the development of this technology. So that's the conclusion of my remarks. The one thing I do want to say is that this project that we're hoping to embark with Masdar will be a single unit like this, 300 to 400 kilowatts. And we're looking for partners to make this happen. This is a very exciting project. This is the future of CSP. And if you or others that you might know might be interested in joining us, the way to do that is, of course, to bring some funding to the table, obviously, in exchange for some preferred pricing and other terms when we are commercializing this, or when you are as a funder. Of course, first mover advantage compared with the competition as we go to commercialize in the future. Insider access to and knowledge about the technology, the performance, where it's going, how it's working, and of course visibility as a sponsor. So happy to meet you and engage with you and join our exciting journey. Thank you.